Hi, I'm Matt, and in this video, I'll explain the solutions to the automatic conversion problems. First, I'll eliminate epsilon transitions from an epsilon NFA to create a regular NFA. Then I'll use subset construction to convert an epsilon NFA into a DFA. Let's begin. Question 1 asks us to eliminate epsilon transitions. The given epsilon NFA has alphabet A, B, 4 states Q0, Q1, Q2, Q3. Start state is Q0 and accepting state Q3. The transitions are Q0 goes to Q1 on epsilon, Q1 loops to itself on A, Q1 goes to Q2 on epsilon, Q2 goes to Q3 on B, and Q3 loops to itself on B. Step 1. Compute epsilon closures. Epsilon closure of a state includes the state itself plus all states reachable via epsilon transitions. For Q0, starting with Q0, we can reach Q1 via epsilon, then Q2 via another epsilon. So epsilon closure of Q0 is Q0, Q1, Q2. For Q1, we can reach Q2 via epsilon. So epsilon closure of Q1 is Q1, Q2. For Q2 and Q3, no epsilon transitions. So their epsilon closures are just themselves. Step 2. Construct new transitions. The formula is delta prime of Q on input A equals epsilon closure of delta of epsilon closure of Q on input A. From Q0 on A, epsilon closure of Q0 is Q0, Q1, Q2. Applying delta on A gives Q1 since only Q1 has an A transition. Epsilon closure of Q1 is Q1, Q2. So delta prime of Q0 on A equals Q1, Q2. From Q0 on B, from Q0, Q1, Q2, only Q2 has a B transition going to Q3. So delta prime of Q0 on B equals Q3. From Q1 on A, epsilon closure of Q1 is Q1, Q2. On A, Q1 goes to Q1. Epsilon closure gives Q1, Q2. From Q1 on B, from Q1, Q2, Q2 goes to Q3 on B. So we get Q3. From Q2, no A transition, so empty set. On B, we get Q3. From Q3, no A transition. On B, we get Q3. Step 3. Identify start and accepting states. Start state remains Q0. For accepting states, we check if epsilon closure of Q0 contains Q3. Epsilon closure of Q0 is Q0, Q1, Q2, which doesn't contain Q3, so Q0 does not become accepting. The accepting state is still just Q3. Why? Same language. The epsilon closure method captures all states reachable via epsilon transitions. New transitions preserve all paths from the original automation. For example, the string AB and the epsilon NFA Q0 goes via epsilon to Q1, reads A, then stays in Q1, goes via epsilon to Q2, reads B, and goes to Q3. Accepted. For example, the string AB in the epsilon NFA, Q0 goes via epsilon to Q1, reads A, and stays in Q1, goes via epsilon to Q2, reads B, and goes to Q3. Accepted. In the new NFA, Q0 reads A and goes to Q1, Q2, then reads B and goes to. In the new NFA, Q0 reads A and goes to Q1, Q2, then reads B and goes to Q3. Accepted. Both automata accept the language, any number of A's followed by at least one P. The epsilon closure algorithm is proven to preserve language equivalence. Question 2. Epsilon NFA to DFA. Question 2 asks us to convert an epsilon NFA to a DFA using subset construction. The given epsilon NFA has alphabet 0, 1, 3 states A, B, C, start state A, and accepting state C. Transitions. A goes to B on epsilon, B loops to itself on 0, B goes to C on 1, and C loops to itself on both 0 and 1. Step 1. Epsilon closure of start state. Epsilon closure of A. From A, we can reach B via epsilon, so epsilon closure of A is AB. Epsilon closure of B is B, and epsilon closure of C is C. The DFA state is AB. Step 2. Apply subset construction. The formula is delta DFA of S on A equals epsilon closure of the union of delta of S on A for all S in S. For state AB on input 0, A has no 0 transition, B goes to B on 0, so we get B. This is a new DFA state. From AB on input 1, A has no 1 transition, B goes to C on 1, so we get C, another new DFA state. From state B on input 0, B goes to B, so we get B. It loops to itself. From B on input 1, B goes to C, so we get C. From state C on input 0, C goes to C, so C. From C on input 1, C goes to C, so C. All reachable DFA states found A, B, B, and C. Step 3. Label DFA states. For clarity, I label these loops as Q0 equals A, B, Q1 equals B, and Q2 equals C. Step 4. Identify accepting states. A DFA is accepting if it contains at least one NFA accepting state. The NFA accepting state is C. Checking. AB contains C. No. B contains C? No. C contains C? Yes. So only C is accepting. Step 5. Why deterministics and equivalent? It's deterministic because each state has exactly one transition for each input symbol, there are no epsilon transitions, and the transition function is complete. It's equivalent because each DFA state represents all possible NFA states simultaneously. Both automata accept the same language, any number of zeros, then at least 1, 1, then any combination of zeros and ones. The subset construction algorithm is proven to guarantee equivalence. To summarize, in question 1, I used epsilon closure to eliminate epsilon transitions, creating an equivalent NFA. In question 2, I used subset construction to create a fully deterministic DFA. Both conversions preserve the accepted language. Thank you for watching.